Beach, and I just want to share with you an article I read about 3 weeks ago showing that there's a direct correlation between these random shootings and inverse correlation between these random shootings and the stability of families. In other words, if you look at families where children are being raised, where the mother and father are there throughout the whole of the time, we see a very low incidence of these mass shootings. And as you know, here in America, we've seen a rapid decline in the standard two-parent family where they remain married throughout the growing up years. You can actually see a graph. There's a direct correlation. And so where do we need to concentrate our legislative efforts? Restoring the strength of our families. So, okay. I've been gone from the class for 2 weeks, and thank you for your prayers while I was back east. And Kathy and I literally got on the airplane just a few hours after we finished all the editorial work on the book that I'm writing on climate stability. So it was a mad rush to get on the airplane, but we got it all done. And our first stop was in Denver, and there I was addressing the Denver chapter, and they need to be commended. They really got a lot of first-time people out there. Over half the audience were first-time visitors. And I really have this class to thank because I spoke on the topic of God, the ultimate darts player. And it's based on some stuff I've taught here in the class over the past year of how there's been these asteroid collisions with the Earth at just the right time, just the right place, with just the right intensity to lead to this incredible period of climate stability that we're currently enjoying. So yeah, God knows how to throw darts, and it hits that bullseye every time. But it's thanks to this class, that was a brand new message I developed, and it's thanks to all the feedback I've gotten here in the class that I was able to develop that talk. So thank you. And the visitors really appreciated that. And then I went on to Atlanta to address a group of people who are presidents and vice presidents of apologetics ministries, and basically spoke about how to reach STEM people for Christ. And I noticed that topic came up in the service this morning. And one of the things I think this church is to be commended for, they're actually introducing children to the STEM topic in terms of science and faith. But it was interesting speaking to this group because most of the evangelists and apologists that are there are still using methods that were very successful 40 and 50 years ago, where you basically present the gospel along the lines of the 4 spiritual laws or 7 steps to peace with God, or taking them through the Roman road. And just communicating to them, we live at a different time, where we have people who no longer believe Hebrews 11:6. 50 years ago, you could count on most American adults actually accepting Hebrews 11:6. I'll quote the passage for you. Anyone who comes to God must believe that he exists, and he wants to reward those who earnestly seek him. Today is different. We have a population, a predominant American population, doesn't believe Hebrews 11:6, which means we need a different approach where we show people that God really does exist. And it's not just any kind of God, it's a God that's got great plans for your life. He wants to reward you as you pursue him. And so just talking to these apologetics leaders about what kind of tools we need to use to reach these people, but also not to get discouraged when your apologetics doesn't work right away. It's something we've seen here in the paradoxes class, that when you get an engineer or a scientist or a technologist who wasn't raised in a Christian home, he comes here to the class, gets interested, it takes about 2 or 3 years before they give their lives to Christ. And I think what's happening is a lot of these evangelists and apologists, they're used to presenting the gospel along the lines of the Romans road and somebody coming to faith in Christ in 10 minutes. That works if people really do believe the God of the Bible exists and they just simply know, how do I get into a relationship with this God? However, it's going to take more than 10 minutes to convince or persuade the typical science-trained or engineering-trained skeptic that there really is the God that exists out there. It's a God of the Bible, and it's a God that matches the description in Hebrews 11:6. And my own personal experience of ministering to these kinds of people over the past 40 years, I've yet to see one that was not raised in a Christian home come to faith in Jesus Christ in less than 2 years after they become interested in checking out the evidence. So that kind of means we've got to do evangelism in a different way if we want to reach those people. And it was interesting, some of the response I got. If it's going to take 2 years, let's just forget it. Let's just focus on the ones where we can get results in just 10 or 20 minutes. But then, and they just said, this is a very small people group. I said, not at all the case. I mean, you can look at surveys done by Barna and Pew, and what you discover is that the younger generation that's coming up, Generation Z and millennials, their desire in terms of a future career is that it would be in a STEM field. For example, they've done surveys of high school students. 52% of students want to pursue a STEM career. And so it said it's not just people in the STEM careers, it's people who are influenced by people in the STEM careers. And if you actually total it up, it adds up to about 1/3 of the whole U.S. adult population. Yes, question?
We don't know what STEM career is.
STEM is an acronym that stands for science, technology, engineering, mathematics, and medicine. So, and I think younger people realize too, well, if I can get into one of those careers, it'll be a secure career, I'll make significant money, and it's going to be interesting. So I'm not at all surprised that we have such a large number of people who want to go in that direction. And as I was able to share with these apologetics leaders, nerds tend to rule society. You may not like nerds, but they're the ones that are generating income, launching businesses, advancing technology. And so if you want to reach the influencers, you need to pay some attention. And yes, it is a lot more work than simply presenting the 4 spiritual laws. But you get to see, and I think there's a myth out there too, that people in these careers are simply not receptive to the Christian faith. They are if you use a right approach. So I got to talk about how you need to understand the culture. And I think what happened is a lot of these evangelists and apologists, they treat people in the STEM careers like they're, quote, regular Americans. So I was able to share with them, actually, you're dealing with a cultural barrier that's at least as severe as if you were to go to a primitive tribe in Irian Jaya where they speak a language you've never heard of before. You need to put it in that context. And I think you've had enough experience here in the Paradoxes class where we've had people come in, and if you're not science trained, you think they're speaking a different language. So, in fact, the latest book that Fuzz Rana has put out, our staff biochemist, it's the first book he wrote that doesn't have 8-syllable words in it. So, it is a different language, and they behave differently. I remember years ago where I invited 6 Caltech physicists to come to this class. None of them were raised in Christian homes. They're all single. And we were studying the book of Titus, and one of them got super excited, ran to the blackboard. We had blackboards back in those days. We don't now. But ran to the blackboard and filled it with equations. And he says, we can actually look at this passage from a mathematical perspective. And naturally assumed that everybody in the class understood all the math he was putting up on the board. And then about a half hour later, too, the physicist says, look, I'm going to defend this interpretation of the text, you defend the other interpretation, and they had what everybody thought was a big fight. And he says, no, we're not fighting, we're just testing different interpretations. But we're testing it very vigorously. Well, non-scientists typically don't behave that way, and scientists do, and so we had an opportunity basically to help those scientists cross the cultural barrier, but help people who are not in the STEM careers also to make that bridge. There is a cultural bridge you have to cross. And when I learned when I was speaking in Atlanta, the vast majority of evangelists, apologetics leaders, simply are not aware of the cultural differences and how we have to change our evangelistic and apologetics approaches to take into account those cultural differences. Yes, Doug.
I keep forgetting to use the mic here. I hope you don't mind, but concerning Fazal Rana, Dr. Rana, last week we were talking about evolution and theistic evolution. Would you say he's just a little more open to that idea than some of the other scholars at RTB? Or, because I've listened to his lectures and it seems like he kind of respects those theistic evolutionists from a scientific point of view.
Well,
and he just has a different point of view, or? Well,
to speak on Fazal's behalf, he respects them, but he doesn't accept their model. I mean, I've known Fuz for 20 years, more than 20 years. In fact, we just celebrated his 20th year on our staff. No way is he a theistic evolutionist. On the other hand, he really wants to equip the church on how to reach theistic evolutionists. And if you simply badmouth their evolution, you're not going to get anywhere. So, and also just to appreciate, there are different definitions of evolution. Often you'll run into research scientists and engineers, for that matter, who will say, evolution is a proven fact. There's no need to debate it. It's proven. What they mean is, it is proven that we have life on planet Earth existing for 3.8 billion years, where it started off simple and progressed to where it became complex. I mean, if you ask the question, are you convinced that it's all naturalistic from one end to the other? Most theistic evolutionists that I've engaged will say, no, we can't claim that. But we can claim that the data is valid. And so, and people, and likewise, I mean, for example, as a graduate student, I took a course in stellar evolution. And so a lot of people think stellar evolution is like biological evolution. Not at all. On the other hand, to understand the history of a star from the time it's born until it goes through its burning phase and becomes a white dwarf, you're looking at about 10 billion years for a typical star. And so it is a long period of time. There's changes. The most fundamental definition of evolution is change with respect to time. Where it gets controversial is when you start speculating what is responsible for the changes. Now, you can look at me, I can show you photos of when I was a little boy. I've evolved over the past number of decades that I've lived. We're all evolving. In fact, the Bible tells us that the entire universe is subject to a pervasive law of decay, which means everything we observe is evolving. And so it's always good to ask, okay, what do you mean by evolution? Incidentally, it works the other way. I'll often be engaging scientists, and they say, oh, you're one of those creationists. And I say, well, what do you mean by creationists? Get them to define their terms. And what they really think is I'm a young Earth creationist. And I say, well, no, there's old Earth creationists, young Earth creationists. In fact, there's a good 15 different definitions of a creationist. And so what one are you thinking about? And so defining terms, I think, is important. So, but yeah, it was just interesting to be there. By the way, a little word for all of you that are live streaming. I've talked to the church leaders here. We are going to be replacing the lights here, because I notice a complaint I've been hearing from people who watch us through live streaming is that the resolution wasn't as good as when we were in the 154 building. Well, the lights were a lot better there. But that's a project that the church has agreed to take on, is provide us with lighting that'll make a high resolution for the people that live stream. And I think today we weren't able to get the splitting to work. So those of you that are live streaming, you're not getting a direct feed of the visuals I'll be showing. We're going to have to use the camera to show them. But I'm hoping that by next week we'll have that all fixed so that you can see the high resolution images. And incidentally, we're going to be fixing this too to make it a little higher resolution. And there's actually some talk about changing the setup in here where we have tables that you can all sit around. which makes it a lot easier for you to enjoy the treats, take notes, get your laptops out there. So some changes are happening, and it should make for, I think, a more inviting experience for visitors as well as for those that are live streaming. But hey, if you got a question, please wait for the microphone. We don't have as good a sound quality here as we had in 154, and in order for the people who are live streaming to hear your question, please wait for the microphone to get to you. So we have a roving mic that will come to you. Well, I've been gone for 2 weeks, and during those 2 weeks, I've been getting a lot of email communications from those of you in the class, and especially from those people that are live streaming saying, please comment on this announcement from the supernova team that there's a big discrepancy in the Big Bang model. And in fact, I can read to you what one individual, in fact, this got picked up by the young Earth creationist community. They wrote an article on this called Big Bang Hubble Contradiction Confirmed. And just to start it off, what happened is a new paper got published in the Astrophysical Journal saying we're seeing, based on Cepheid variable stars and supernova, that the rate at which the universe expands is higher than the rate that we see based on cosmic background radiation maps. And they say it's a significant discrepancy. Now, the difference is only a few percent, but the accuracy with which they're measuring these is such that people say there's a discrepancy. Now, the people who wrote the paper basically said this is going to lead us to coming up with a more detailed Big Bang creation model. However, the young Earth creationists responded to this by saying this shows that the Big Bang model is wrong. And incidentally, this has been a long history of what we see in the young Earth community. Every time astronomers are seeing what they call an anomaly, they say that means the model is wrong. I'll give you a couple of quotes from what got published at the Institute for Creation Research. What they're really targeting is that the Big Bang model is dependent on the redshifts of distant galaxies. And they basically imply that the entire Big Bang creation model depends on these redshift measurements. I can tell you that is false. It is some of the evidence, but it's actually not the most compelling evidence for the Big Bang model. And incidentally, my peers do refer to it as a creation model because it talks about the beginning of the universe. In fact, my colleagues are rather mystified why Christians think the Big Bang model is wrong or an enemy, because they say, you know, we never liked this model because it had such strong Christian implications. And why are Christians throwing out this model? They just can't understand that. But the whole point of this article put up by the Institute of Creation Research is that we have two different measurements of the cosmic expansion rate, and they disagree. And scientists have known about this contradiction for years. And they make this quote from the principal author of the paper, Adam Rice, who said, quote, "The Hubble tension between the early and late universe measurements may be the most exciting development in cosmology in decades." And the response of the young Earth creationists is, quote, "Most professions being wrong over and over again isn't usually seen as exciting." And they conclude with this: if the results agree with Big Bang expectations, quote, which they almost never do, then this is claimed as a victory for the Big Bang. If the results disagree with Big Bang expectations, this isn't acknowledged as evidence against the model, but rather chalked up as evidence for some undiscovered physics to be added to the model. And that's been going on now for 40 years. In fact, 40 years ago, people were saying, well, when we look at maps of the cosmic background radiation, we see no details. And if the Big Bang is going to lead to galaxies, there should be details. Therefore, the Big Bang model must be tossed out. Astronomers at that time were saying, we don't expect to see details on a coarse scale. We only expect to see them on a fine scale, and we don't have the instrumentation to see it. The COBE satellite was the first time they were able to map the cosmic background radiation where they could get down to those fine details, and they saw the fine details that the Big Bang model predicted. But yeah, there was this big cry out, the Big Bang model is in trouble. Well, it was in trouble because we lacked the instrumentation to detect the prediction. And then a few years later, it became clear that the cosmic expansion rate wasn't matching the ages of the stars. In fact, we were basically showing that the stars were about 1 billion years older than the universe. They said that means the Big Bang model is wrong. All astronomers were saying it means that there's systematic errors we're seeing in our dates for the oldest stars, or there's systematic errors we're seeing in our dates for the universe. We need to study this in more detail. It took about 10 to 15 years, but finally they got the universe to be older than the stars. But again, there was this loud cry, the Big Bang model is wrong, it needs to be tossed out. And then they were seeing that the universe was expanding at a rate that was inconsistent with the mass of the universe. And there just wasn't enough mass in the universe to explain why it was expanding as rapidly as it did. And that means the Big Bang model is wrong, we need to toss it out. The response of the astronomers was, maybe there's some dark energy that we haven't taken into account because you don't have the capacity to measure it. Again, it was a 20-year effort. For 20 years, astronomers were predicting, we're going to find this dark energy. It wasn't found until 1999. But what they found was exactly what you would need to explain the cosmic expansion rate. And then after that, there was a comment, well, the matter that we can easily measure doesn't account for what the expansion rate is. Again, the response of the astronomers is, well, there's two kinds of matter, ordinary matter and exotic matter. And again, it was about a 20-year effort to basically establish, yes, there really is exotic matter. Now, to get kind of down to a bottom line on this, what is happening is we started in the early part of the 20th century with a simple Big Bang model. The universe expands from the beginning, and the expansion rate is controlled by the mass of the galaxies that we see. But as the model began to progress, we said, well, there's actually galaxies farther away than what we see, and they have an influence on the cosmic expansion rate. And so what's been happening is the Big Bang creation model is becoming more and more detailed and more refined. And you've heard of Occam's razor. The answer you want to go with initially is the one that is the simplest. And that's how science works. We begin with the simplest explanation of the phenomena. However, science, the history of science is the simplest answer is never correct. It's always more complicated than what you see. But by focusing on the simplest answer, it allows you to understand and do the observations, experiments, to see the missing details. And so the actual history of Big Bang cosmology is that our model is becoming more and more specific. We've gone from a general model to a highly specific model. And this paper was just published is basically making the point. We've done 80 years of research on Big Bang cosmology, and the model that seems to be best fitting the model, and keep in mind, we've gone through over 30 different Big Bang creation models, but they're all Big Bang creation models, every one of them. And but the model that's been predominant is what's called the lambda CDM model. Astronomers love acronyms. In fact, we don't do an experiment until we first come up with an acronym. So actually we all sit around and figure out what kind of acronym will sound good to the lay public, to the people who give us the money, and then we actually begin the experiment. The lambda, which is the Greek letter for capital L, stands for dark energy, and it's at the front of the acronym because the measurements tell us dark energy is the predominant component of the universe. It makes up about 70% of all the stuff of the universe. And then CDM stands for cold dark matter. And so it's basically saying that it appears from our measurements that the matter in the universe is moving at low velocities relative to the velocity of light. And so hot dark matter is matter moving very close to the velocity of light. Warm dark matter is matter that's moving somewhere in between 0 and the velocity of light. And cold dark matter means they're moving at low velocities. And so that's been the predominant Big Bang creation model, the lambda CDM model. And this paper is basically saying it looks like we may have to refine this lambda CDM model. It will still be a lambda CDM model, but we're probably going to be adding a couple more letters to the acronym. That's kind of what's happening in this paper. But what I want to show you is the actual discrepancy. And I'm going to write an article on this. I thought, this is so obvious that it's just a small discrepancy. Why bother writing an article on this? But because there's been such a big furor over this in the Christian community, I am going to be writing an article on this. Now, these are the best measurements of the cosmic expansion rate. And the units at the end there are in kilometers per second per megaparsec. You say, what on earth is that? Well, I think you all know a kilometer is about 0.6 of a mile. A megaparsec is 3.25 million light years. So it's basically saying every 3.25 million light years you go out, you get a velocity increase of about 72 kilometers per second. And I put all the error bars on the right side, and those error bars are intended to include the random errors and the systematic errors. You say, what are the differences? Okay, the random errors, are where you're making a bunch of measurements, and it's basically the deviation you see in the different measurements that you make. But on top of that, there's systematic errors, basically saying you may be using an instrument that shifts the measurements slightly one direction or the other. Or you may be overlooking an effect that may be influencing your measurement. And those are referred to as systematic errors. And astronomy and physics and geophysics are about the only sciences where we actually have a good handle on systematic errors. If you read the life sciences, they really don't address systematic errors because they haven't got a clue what they are or how big they are in most cases. But as you can see, these measurements roughly agree. However, what this paper is pointing out, if we look at the two extreme ends, and this next slide shows you that, you basically have got the measurement of the cosmic expansion rate from the Planck map of the cosmic background radiation, and you got what are called the baryon acoustic oscillations. They're coming in at 67.3, and this latest paper is one at the bottom, where they come in with a measurement at 74. And they said the difference is a little more than 6 kilometers per second per megaparsec, but notice how small the error bars are. And they're basically saying the difference can't be explained by the error bars. It seems to be bigger than what the error bars would allow, and therefore there's some unseen physics we're not fully taking into account. Now, I do want to point out, however, that the difference may not be as big as what this paper claims, because we have the W map of the cosmic background radiation looking at the same data, and they come up with 69.3. And likewise, we see that the most recent published measurement for the cosmic expansion rate based on Cepheid variables and type 1a supernova was 70.6. If you compare 70.6 with 69.3, they're well within the error bars. So basically saying even using the same method, you're getting different answers. And having read this paper, what they did that no one else had done before was to establish the distance to the Large Magellanic Cloud. You say, what's that? that's the nearest galaxy to our galaxy. Just beyond our Milky Way galaxy are two large dwarf galaxies, the Large Magellanic Cloud and the Small Magellanic Cloud. And the Large Magellanic Cloud is about 6% the size of our galaxy. It's actually kind of an irregular spiral galaxy. I should have shown you a photo here. I could dig it up, but it would take too much time. But being nearby, astronomers are able to look at what are called eclipsing binary stars. These are two stars that are orbiting about one another, but they're orbiting about one another far enough away from one another that astronomers can measure the angular diameter of the orbit. And they can also measure the speed with which the stars are going around one another. And according to Newton's laws of motion, the rate at which a star goes around another star will depend on the distance between the stars. And so if you can measure the rate, that tells you how many miles exist between the two stars. And if you measure the angle, then that can tell you how far away they are just by using plane geometry. And maybe I need to show you that in case some of you have forgotten your high school geometry. I think I've got a slide that actually shows you that. Yeah, here we go. Do you remember this when you took high school geometry? Where that's an isosceles triangle, where the two sides on either side are equal. And there's a theorem that says if you measure the base of the triangle and the two angles with high precision, that tells you the distance to the vertex. So this is a technique you can use to measure distances to stars and galaxies. And so in the case of these eclipsing binary stars, the base of the triangle is the distance between the two stars that you see there. And then by measuring the rate at which they're going around, they know what that dimension is. And from far away, you can measure the angular separation of the two stars. It's actually the reverse of this, where your telescope is at the vertex and you're measuring the diameter of the orbit. Bottom line, you're getting a direct distance to the Large Magellanic Cloud. Zero assumptions. So you know without making any assumptions exactly how far away that is. And they've done this previously, but the best effort done previously is they used 20 such binary stars in the Large Magellanic Cloud. What's new here is they've done it with 20. 20 different binary stars in the Large Magellanic Cloud, and they're able to publish the most accurate distance to date to the Large Magellanic Cloud. And say, well, what's the big deal there? Okay, the Large Magellanic Cloud is filled with Cepheid variable stars. Anybody here ever heard of a Cepheid variable star? Okay, we got two people here who've heard of a Cepheid variable star. Actually, there's a star in the constellation Cepheus that you can watch tonight. And if you watch it over the course of, say, 4 or 5 days, you know that it changes in brightness. It gets brighter, then it gets dimmer. It gets brighter, then it gets dimmer with a regular period. In fact, we can measure the period of these Cepheid variables to very high precision. And what they've discovered is the period of these stars is directly proportional to its luminosity. And so the longer the period, the brighter the star, which means if you can measure the period, you know the brightness of the star. And if you know the brightness of a Cepheid variable in the Large Magellanic Cloud compared to a nearby one in our galaxy, that again tells you how far away the Large Magellanic Cloud is. And basically the paper was saying we can use the Cepheid variable method and we get the same answer for the distance of the Large Magellanic Cloud that we get using trigonometric parallel, using this high school geometry theorem. And then they bootstrapped that because now, thanks to the Hubble Space Telescope, we can see Cepheid variable stars as far away as 40 million light years, which means we can see in a lot of different galaxies. And again, the universe is expanding, so galaxies farther and farther away will expand at a higher and higher rate, and hence they publish this value that you see here saying, we believe this value of 74.0 is the most accurate measurement of the expansion rate of the universe. However, reading this paper, I went back to the previous paper and noticed the error bar is a little bit bigger, plus or minus 2.6 as opposed to plus or minus 1.4. But one thing I did notice in this previous paper is they did a detailed analysis of what they call the systematic error of taking into account the star formation rate. Basically pointing out the rate at which stars form in a galaxy makes a slight influence on the measurement you're going to get for the cosmic expansion rate. It actually drops a little bit. So that's something that's worth studying. If we actually look at that in some detail, which of these two measurements is accurate, and maybe that 74 will drop a little bit, maybe it won't, but that's something that needs to be checked out. And also going back to that old measurement, say, to what degree is that low number impacted by the fact that they were only looking at 8 eclipsing variable stars. And incidentally, the authors of this paper are making that point. It says, we need to check these things out to see how real this discrepancy really is. Yes, Doug?
How does the cosmic expansion rate compare to the speed of light?
Well, it depends how far away you look. The farther away you look, the faster those galaxies appear to be moving away from us. And if you look all the way back to the beginning of the universe, in other words, the farthest reaches of the universe that we can observe, those objects are moving away from us at just under the velocity of light. But for example, as we make measurements inside our local group of galaxies, the motions of the galaxies by the gravitational interactions actually dominate the expansion of the universe. So you really only see the effect of the cosmic expansion when you get beyond the very nearby galaxies. But once you get out of the Virgo cluster, it's very easy to see.
Well,
in fact, only 2 galaxies we observe are blue shifted. Everything else is red shifted.
Well, one of the things that's confusing me, probably because I'm not an astronomer, but how could an object be 40 million light years away from us or from whatever when the universe is 14 or 13.79 billion years old?
Well, if the universe is 13.8 billion years old, you're going to be able to observe galaxies anywhere from 0 out to about 13 billion light years. And so we're talking about galaxies that are only 40 million light years away. And it's in those galaxies we're able to see these Cepheid variable stars. Cepheid variable stars are bright stars, but there reaches a point where our telescope power is no longer able to accurately measure the rate at which they vary. And so 40 million years is about the limit. However, if we go out 40 million light years, we're going to find a lot of galaxies that not only have Cepheid variable stars in them, they also have these type 1a supernovae. And just like Cepheid variable stars are standard candles, which means if you see one in one galaxy, and if you find another one in another galaxy, you can count on the fact that they're the same brightness. So simply looking at the brightness difference tells you the difference in the distances. I mean, a standard law of physics is if you take a light bulb and move it twice as far away, it'll appear to you to be 4 times dimmer. And so just using that law that the brightness goes down with the square of the distance, by comparing the 2 brightnesses, you can tell how much farther one is away than the other. Well, what we discover, it is true that some supernovae are brighter than others, but all type 1a supernovae have the same brightness. So a subset of the supernova are what we call standard candles. All type 1a supernova have the same brightness. Now, they're much brighter than Cepheid variable stars. And so we're able to see them as far away as 8 or 9 billion light years. And so using the Cepheid variable stars to calibrate the brightness of these type 1a supernova, we can actually extend this measurement out to about 8 billion light years. Okay, question from Steve.
I'm going to focus on redshift. I don't know if any of these expansion rates depend upon redshift, but if we could notice a redshift on a standard candles and the redshift differs, could we use that redshift to bring the furthest standard candle back to a beginning point in time compared to the other standard candle and come up with the time of origin?
Yeah, that's exactly what astronomers do.
Okay.
They basically use Cepheid variable stars and type 1a supernova to demonstrate that the redshift method is a reliable indicator of the cosmic expansion rate and hence the age of the universe. And when young Earth creationists critique this, they're overlooking the fact that we now have direct distance measurements where we use that high school geometry theorem that take us out to 500 million light years. There's actually a galaxy that we've been able to measure. In fact, you see there where it says masers in NGC 4258 and masers in 3 other galaxies. These are galaxies that have got these very bright, compact maser sources that are orbiting about the center of the galaxy. So this is similar to the eclipsing variable stars, or the eclipsing binary stars, in the sense that you've got this maser that's orbiting about the center of the galaxy, and you can measure the size of the orbit, the angular size, and we can measure the rate at which the maser is going around the center of the galaxy, and through Newton's laws that tells us the actual number of miles that about the diameter of the orbit, and by comparing that with the angular measurement, we can actually determine, without any assumptions, the distance to that galaxy. But the farthest galaxy away where we can see these kinds of masers and make those measurements with adequate precision is just a hair under 500 million light years away. But that means we can calibrate the redshift method over the first 500 million years.
And so to really drill down on this, for my need, is that once we've established the angle and the distance and miles and so forth, then we can add on to that seemingly the redshift difference that would have happened and bring that back to a 0 point of
Right.
13.8. Okay.
Well, I mean, maybe I need to just share with us, the inverse of that number of 70, 69, whatever, gives you the age of the universe. Now, that's assuming that the cosmic expansion rate doesn't change. But that's one thing this paper is pointing out. He says, notice the measurements that are giving you a high value are based on measuring the cosmic expansion rate in the nearby universe. The measurements that are giving you a low value, the baryon acoustic oscillation and maps of the cosmic background radiation, that's giving you the measure of the cosmic expansion rate when the universe is very young. And so they said it could be that the cosmic expansion rate varies more than we think it does. Now, we already know it must vary at least somewhat, as what we see here, because dark energy gets more and more powerful to accelerate the expansion of the universe as the universe gets bigger and bigger. And gravity works the other way. When the universe is small, the different pieces of mass are close together, and hence gravity will be stronger in slowing down the cosmic expansion rate. So it's well known in the astronomical community that we anticipate we're going to get a slower cosmic expansion rate when we're looking at, say, the first billion years of the history of the universe, or the first million years, than we would if we look at the last billion years of the history of the universe. So we do expect there will be a difference, but the authors of this paper are pointing out it's a bigger difference than what we anticipate. And we could handle a difference of, say, 1 kilometer per second per megaparsec. In fact, The standard lambda CDM model predicts about a 1% difference. The problem is we're seeing about a 6% difference. But again, I want to alert you to the fact that there may be systematics we're overlooking. For example, the method based on masers is a direct measurement. However, notice a discrepancy. You've got 72 based on NGC 4258, and you've got 67.6 based on 3 other galaxies. Those 3 other galaxies are farther away, but we wouldn't expect a difference that big. So again, it's telling us we're overlooking some systematic effect. On the other hand, it might be random. Notice the random is plus or minus 6 for those 3 and plus or minus 3. So people could say, well, there really isn't a significant difference between the 67 and 72. On the other hand, that difference is roughly comparable to what they're pointing out in this paper. So that needs to be looked into. I saw a hand somewhere here. Yes, we need to get you the microphone.
So what would the graph of the different rates look like if on the x-axis distance of measurement was made?
Well,
And
okay.
then y-axis being rate of expansion.
The paper is also pointing out we need to get that James Webb Telescope orbited. It's been delayed almost 10 years now, but that's an instrument that can help us fill in a lot of the data that we're missing. Basically, we've got good measurements of the cosmic expansion rate from the present to about 5 billion years ago. And we've got good measurements for the first 500 million years of the existence of the universe. But there's a gap where we do have measurements, but they're not accurate measurements. And so they're saying with the James Webb Telescope, we might be able to get accurate measurements all the way through and then be able to produce the graph that you're talking about. What is the cosmic expansion rate relative to distance or relative to the history of the universe? As I say, the model that's most popular today predicts about a 1% difference, and the paper concludes saying, if this 6% difference is real, this is what they're concluding. Let me actually get their final statement here. Oh, here it is. They say the tension between the early and late universe, in other words, between the measurements we get in the early history of the universe and the measurements we get in the present history of the universe, the late universe, may be interpreted as one of the following: as evidence for a new cosmological feature, such as exotic dark energy, a new relativistic particle, dark matter radiation, or neutrino-neutrino interactions, dark matter decay, or a small curvature in the geometry of the universe. Basically saying we can refine the lambda CDM model with 1 or 2 or 3 of these small adjustments that could be made to the model. And they said this is an exciting discovery because if this discrepancy proves real, we may be able to produce an even more detailed Big Bang creation model than we have today. And the reason why I think this is important to talk about, the Bible was the first book to talk about Big Bang cosmology. My young Earth creationist friends may not like this, but I think it's easy to document that if you go through the Old Testament, what you see are repeated statements that the universe has a beginning. And it's not just a beginning of matter and energy, it's a beginning of space and time itself, which implies an agent beyond space, time, matter, and energy that created it. And there are 11 texts in the Old Testament that tell us that the universe expands from that space-time beginning, that it expands under laws of physics that don't change, where one of those laws of physics is a pervasive law of decay. I mean, you see that especially in Jeremiah 33 and the book of Ecclesiastes. The way God designed the universe, everything is decaying. If you don't believe that, look at one another, okay? We're all in a process of decay. Our backyards are in the process of decay. Our automobiles are in the process of decay. Stars are in the process of decay. The good news is this: the stars are decaying much more efficiently than you and I are decaying. But the decay is everywhere. And that implies that the universe must get colder and colder as it gets older and older. Because of thermodynamics, any system that expands gets colder as that system expands. That's how your automobile engine works. As a piston chamber expands, your gasoline stops burning because the chamber is now so big that the temperature drops and stops the gasoline from burning. When you compress the piston, the temperature goes back up. If you've got a diesel engine in your car, you don't even need spark plugs because there the piston chamber compresses so much it raises the temperature to the ignition point of the gasoline. And so the Bible was the first book to talk about Big Bang cosmology. And incidentally, just this weekend, I was involved in a Twitter debate over this whole point saying, well, that's just you, a 21st century astronomer, reading this into the text. I mean, you think those texts are literal. We think they're just figurative. It's not talking about Big Bang cosmology at all. Well, a good response to that is you've got Jewish theologians 800, 900, 1,000 years ago seeing these same things in the biblical text, which argues that they're really not figurative. The Bible literally is speaking about the universe having these characteristics. And I think what excites me is the more we learn about the universe, the more detailed Big Bang creation model we get. And that's always evidence that you're on the pathway to truth. Quite counter to what I see from my young earth friends that say every time they come with a more detailed model that shows the model's in trouble. No, that's not how science works. The more detailed you make your model, the more evidence you have that that model is correct. Get the microphone over to Steve, please.
Thank you. I want to piggyback on the last question on the X and Y graph. And on X, what would that mean, I think, for the time of the universe of 13.8 billion years compared to each one of these Hubble constants? If each of these Hubble constants on its inverse gives a different time for the universe, which Hubble constants gives us 13.8 billion years? And the difference between the lowest number up here of 67.3 and the highest number of 74 is 9%. So if I pegged a hypothetical here on the 13.8 billion years being at 74 Hubble constant, then 9% less for the lowest number would be 12.5 billion years. So how do we combine whatever we're combining on Hubble constants to get to 13.8?
Okay, well, the Planck measurements are basically telling you what the cosmic expansion rate was when the universe was 380,000 years old. So it's giving you the expansion rate when it was that young. Whereas this paper I got here is giving you the expansion rate over, say, the past 5 billion years. And so that's one reason why they end their paper saying we may be actually looking at a real difference between the cosmic expansion rate when it's young and the cosmic expansion rate that it has right now. And as we've mentioned, that fits what we'd expect from gravity and dark energy. But notice they made the point here that this 9% difference is so large that it would imply, what have I got here? Sorry, I got my pages mixed up here. Here it is. Nope. Just a minute. Oh, I have it right here, sorry. Yeah, the first thing they're suggesting is maybe we're looking at exotic dark energy rather than simple dark energy. The predominant, what they call the lambda CDM model, assumes that dark energy is governed by a single constant. You may have heard of the cosmological constant. It was something that Einstein suggested when he first put his theory of general relativity. And so that's kind of the simplest explanation of dark energy. It's governed by a single constant. What they mean by exotic dark energy there may be 2 or 3 constants governing dark energy, not just a single constant. And if we got more than one constant, that could explain why we're getting a 9% difference rather than just a 1 or 2% difference. So that's probably the first thing we're going to be looking. By the way, that's been a quest of astronomers for the past 15 years to determine whether dark energy is governed by a single cosmological constant or if it's more complicated than that. There's already enough evidence in the astrophysical literature that tells us it seems like we're moving towards a slight complication, not a major complication, because very roughly it looks like a single constant does it, but not exactly. So that could account for some of the adjustment, but I think that's what's commendable about this paper. They're not putting all their eggs in that one basket, because I'd agree with them. It's unlikely that adopting an exotic dark energy model is going to solve the discrepancy, which is why they mention these other things, like exotic dark matter decay. That again has been a quest of astronomers looking over the past couple of decades. Are there dark matter particles that are decaying in such a way that it would affect the cosmic expansion rate? Okay.
Thank you for that answer of having expected different expansion rates for earlier or later parts of the universe. With that being the case and with the errors that we have, how certain can we be of the 13.8 billion year error? Should we have error bars for error bars? And just what does this do to that certainty?
Well, that's what young Earth creationists have jumped on. They said if that 74.0 figure is right, we're looking at a universe that's only 13 billion years old, not 13.8 billion years old, or maybe even just 12.8 billion years old. And basically saying astronomers don't know what they're doing.
So where's our confidence?
Yeah, in other words, they're saying astronomers are incompetent, they just can't come up with these numbers. Well, when I was an undergraduate student, the date we had for the age of the universe was between 10 and 20 billion years. So I'm kind of excited that we've gone from an error bar of 100% to an error bar of less than 10%. But the goal in cosmology is to drive that error bar down to something close to 1%. And for example, the WMAP measurement is actually quoting a measurement that's very close to just 1% accuracy. So we're going there, but the reason why I put this up here, that 9% difference may in part be simply due to the fact that we're overlooking some systematic effects. Although I do think the authors have a case that we're probably not going to get rid of it entirely by simply examining the systematics. That might lower the discrepancy, but it's probably not going to eliminate the discrepancy, which means we already are looking at something to add to the lambda CDM. So bottom line, I'm predicting a couple of years from now, there'll probably be 2 more letters we'll be adding to that acronym. But it's still a predominantly lambda CDM model, just that we're going to have measurements that will give us more detail on the Big Bang creation model than we have today. But I'm a little bit disturbed that certain Christians actually look at this as a failure of science and basically saying, this is proof you can't trust scientists to give us any real knowledge of the truth of the universe. Actually, it's quite the opposite. Astronomers and physicists are giving us a more and more accurate picture of the universe as they learn more and more, and we shouldn't be surprised that the model goes from something simple to something more complex. I mean, every field of science has witnessed that. We hope things are simple. We always discover that they're a little more complicated than what we thought. By the way, that's even true in medicine. We're discovering that the human body is more complicated than what we thought even 10 or 20 years ago. We got living evidence of this, right? But the amazing thing is, as we learn more and more about the human body, we discover more and more of how amazingly it's designed to allow us to function at a high level of competency for 8 or 9 decades. I mean, there's no other animal on the face of the earth that's able to perform at the level that we human beings do. And what's amazing about that, typically, the bigger the body size, then the less productivity you get. We have a big body size, and yet we get to live as long as we do and be as productive as we are, even in spite of the fact that sometimes we have a bad diet and don't exercise our mind or our muscles as we must want to do, okay? Yeah, and all of our bad habits. It's like God, I think, anticipated that we would be sinners and do things that are rather stupid to do, but gave us a body that could actually handle that. Not that I'm recommending you do stupid things. Okay. Question over here.
Just wanted to go back to one of your statements earlier about Occam's razor. Now, when I'm talking with my atheist friends at JPL, they're using that against me, like, this idea that God's a very complex idea, so Occam's razor is pointing away from that. But the way you stated it, I hadn't thought of before, that was just something you start with
Right.
as a scientist, and maybe you can kind of expand on exactly
I
how
think
that's used.
you're raising something interesting, Steve, and in that atheists love to use Occam's razor as a weapon against Christian belief systems. But what I'm arguing is that they're misusing Occam's razor. Incidentally, Occam was a Christian, a very committed Christian. And so his point was, always start with the simplest explanation. That way you're not going to be going on a model that's way off the truth. It's going to be roughly focused on it. But you anticipate that your beginning simple model will become progressively more and more complicated as time goes on. But the way I've seen atheists use Occam's razor is saying, when you appeal to God, you're appealing to something much more complicated than just physics and chemistry doing everything. Well, that can be tested. Can physics and chemistry really explain everything? And if it can't, then you have to abandon that explanation and go with something that's more complicated. Because what happens is if it's just physics and chemistry, you can explain the simple stuff, but you can't explain the complicated stuff. So don't be surprised you got to come up with a more complicated causal agent because you're dealing with something more complex. And the way I use that with my atheist scientist friends is say, well, let's pick the origin of life as a starting point. Okay, because basically you've got, there's a quote if you want to see it. Basically, you're saying physics and chemistry can explain how we go from hydrogen, carbon, oxygen, and nitrogen to getting a functional bacterium. Well, can physics and chemistry really do that? In fact, another article I'm going to be writing, this one it just blew me away, got published in Nature about 2 months ago. And the title of the paper was The Hand of God Fallacy. I was basically referring to the fact that these chemists get into these labs and are saying, look, we can make an amino acid just from these simple molecules. And we can actually get a couple of these amino acids to come together. And we can actually select for some limited degree of homochirality. And hey, we can actually make a ribose sugar. However, the only way that works is if you've got a chemist with a PhD education and a lot of federal funding and a high technology lab to make it work. It's not really showing you how it happened in the real world with just physics and chemistry. There's the hand of God, and basically what this author is pointing, he's not a believer by any means, but he's saying, notice that in all these experiments, you need a highly educated, highly intelligent, highly funded scientist to make the reaction work. Take that scientist out of the picture, and all of his technology and funding, nothing happens. And so that's what's being referred to. But it's the first time I've actually seen that in the scientific literature. And I'm pleased that they're actually calling it the hand of God fallacy. Because basically it's making the point, if a biochemist can't do it with all that funding and education and the technology, then clearly it was done by somebody who's even more intelligent, better educated, with more power at its disposal than what the National Research Council can provide for them, or the National Science Foundation. So that's how I would respond. Just say, let's pick something really simple, like how do you get a bacterium? I mean, the human body is orders of magnitudes more complicated. Or for that matter, how do you explain our Milky Way galaxy? I mean, that's really simple, but all the naturalistic explanations for why it has the features that it does to make advanced life possible simply fail. So you can push that again and again. Okay. But yeah, what they're pointing out is we think we're on our way to actually establishing that one of these cosmological features actually exists. And what I like about the paper, it's almost certain that one of these plays a role in describing the why our universe looks the way that it does. And in each case, we got a team of astrophysicists that are busy searching for one of these. And you know, what could really play out is that maybe all of them are right. Maybe each one plays a small role, and maybe that explains why we've not been successful in nailing any of these down. Because if each one plays some small role, it's going to be extremely difficult, given our technology, to actually establish that this is a real phenomenon. So it could well be that what this paper is pointing out could remain unsolved for the next decade. So, but also, they also end with an appeal to you, the taxpayer. Give us more funding, we can make the instruments that'll settle all these amazing questions for you. So assuming, of course, that the public actually cares about these things being resolved. Yes, Doug.
Probably you could give me a short answer for this. In my reading, I'm still unclear about the locale of dark matter and dark energy. Are they in the same locale?
No, they're not.
And what distinguishes them from one another? I mean, is there a relationship? Obviously, matter's different than energy, but I mean, are they correlated in some way?
Astronomers believe that they're independent of one another, that dark energy is unrelated to electromagnetic energy. It's not heat, it's not light.
Yeah.
It's energy that's embedded in the space surface of the universe, the space fabric, or what they like to call the manifold of the universe, which is basically the space-time surface of the universe.
The outer surface, like?
And, well, I mean, I'll give you an analogy. You know, think of planet Earth. It's 3 dimensions, but we humans live on the 2-dimensional surface of the 3-dimensional Earth. And so what they're basically saying is dark energy has the same value everywhere you measure it on the surface. There is no inhomogeneity to the dark energy. It's the same everywhere on the surface. But as the surface gets bigger and bigger, as the universe expands, dark energy becomes more and more powerful, because it's the dark energy per unit area that really factors. Now, it makes this quite complicated and difficult to visualize. The surface of the universe is 3 dimensions, not 2 dimensions. So the planet Earth analogy breaks down, and if the Earth is only 3 dimensions, the universe is 4 dimensions. And the surface of the universe is a 3-dimensional surface of a 4-dimensional expanding universe. The dark matter, on the other hand, does have inhomogeneities. Basically, you see the dark matter being clumped, and where most of it exists is in giant halos around the galaxies.
Okay, so is there dark matter or dark energy in the center of galaxies?
Well, to give you an example, what makes our Milky Way galaxy such an exceptional galaxy is about 90% of its mass is dark matter. And so very different than what you see with the Andromeda galaxy, which has much more of its mass in the form of stars and gas. Ours has less in the form of stars and gas, but more in the form of this dark energy. And that explains why we have such stable, symmetrical spiral arms. One of the reasons why we have such stable. You say, well, how did we get that extra dark energy? This just got published a month ago. A couple of papers got published saying that when galaxies merge together, the bigger galaxy will often take away the dark matter from the smaller galaxy and keep that. And so if you get the right merger history, you can actually have much more dark matter in your galaxy than would be typical for other galaxies. But the unusual thing is we know our Milky Way galaxy did not have any major merging events for the last 10 million years. So this is something that must have happened in the early history of our Milky Way galaxy. But they must have been quite significant mergers to enable us to get that much dark matter.
You mentioned there are 4 dimensions of space. What are those?
Okay. general relativity tells us that the time dimension on large cosmic scales takes on the features of a space dimension. And so we speak about the 4 space-time dimensions of the universe. In other words, the time dimension actually can be considered a 4th geometrical dimension because there's a link between space and time in the theory of general relativity. And we got measurements to show that that really is the case. But that means you really can't visualize what the universe really looks like. You know, when people talk about where's the center of the universe, well, that's like saying if you're constrained to the surface of the Earth, where's the center of the Earth? If you can't observe in that dimension, you don't know where it is. They used to say London was the center of the Earth, but now probably some other place. Okay. All right. I didn't mean to spend so much time on this, but it is relevant in the sense that we're going to be diving into Isaiah and what it says about the flat Earth and about geocentrism. I'm adding that question mainly because I've been watching on Facebook and Twitter. It seems like the geocentric model has seen a huge upsurge within the Christian community as well as the flat Earth model. So I'm going to suggest that we look at Isaiah and what can we do to counter that, because what's interesting, both groups are citing Isaiah as proof of their position. And so the question you'll see in your sheet, and by the way, if you don't have it, I'm going to hand it out. Now, there were some questions on our study of Isaiah that have to do with end times prophecy. I'm going to jump over that and get to the question we have on the shape of the Earth and the structure of the solar system. But what I've been noticing on Facebook and Twitter is that we seem to have a situation in the American population today where people have forgotten their high school geometry. If I can bring it back down. I'll jump down to this one. This is an application of your high school geometry theorem, but it basically shows how you can determine how far away the sun is, how far away the moon is, how far away the stars are. Now, this assumes, of course, that you actually believe that the Earth revolves around the sun. If the Earth revolves around the sun, you can make an observation of the star in December, make another one in June, and that gives you a baseline of 186 million miles for the bottom of the triangle, and you can measure how the position of the star appears to change relative to background objects. And typically what we do in astronomy, it's not just distant stars, we look at distant quasars. So we're looking at objects that are 12, 13 billion light years away, sufficiently distant that we don't have to worry about the parallax of those objects. But what we notice is the position of the star will appear to change. So just like there's a parallax effect, that's why we got 2 eyes. The reason why you got 3D vision is because of that high school geometry theorem. This is the base of your triangle, and as you look far away, you can determine how far away an object is. And it actually works quite well with our eyes, in the sense that I can tell how far away each of you are sitting from me, just because I got 2 eyes instead of a single eye. If you're missing an eye, you can't do that. You can't determine distances. But with 2 eyes, you can. Same principle is used here to determine this. But what I've been noticing in the flack I've been getting on Facebook and Twitter, by the way, I can see both atheists and Christians pushing this viewpoint that astronomers and physicists have it all wrong. The Earth isn't a sphere, it's really a flat disk, and the sun goes around us. We don't go around the sun. And they're basically saying astronomers have got it all wrong. The stars are not far away, they're really close. And I'm basically making the point, hey, if you remember your high school geometry, that's all easy to refute. And also making the claim the ancients had no idea what the universe looked like, or what a solar system looked like. We're going to talk about, oh, I'm almost out of time. Okay. The reason why I want to do this for you is I want all of you to be equipped to basically take what you learned when you were in grade 10 studying these theorems and actually be able to apply it to help people realize that, there isn't a grand conspiracy amongst scientists to fool us about the fact that we live on a spherical Earth. And you'll enjoy this. They say, well, where's the edge? They claim the edge is Antarctica, that we live on this flat disk, and the edge is Antarctica. And so when you go to Antarctica, you always find ice no matter how far you go. People have actually crossed Antarctica. But what I'm going to do is basically, this is your homework assignment. You run into somebody who insists there's a conspiracy amongst scientists, and we've been fooled all these hundreds of years into thinking the Earth is a sphere when in fact it's flat. How do you refute that? And here's a second assignment. You run into somebody who says geocentrism is the way to go. The sun's not the center of the solar system. The Earth is the center of the solar system. How do you refute that? And I want you to come up with refutations that are at a lay level, okay? It's easy to come up with responses that the person you're talking to has no idea what you're talking about. I want you to come up with something at a lay level. And the reason I'm spending time on this, I think this is a growing phenomenon. And I think one reason for it is we have a lot of people going public claiming to be experts in a discipline when in fact they're not experts. And people find out, wow, what they're saying is not correct, and they actually apply that to the whole scientific community. I think that's a problem with the American media, is they bring people on to talk about something, and people think they're experts when in fact they're not actually trained in that particular discipline. And I've talked to people in the media, and they say, well, there's actually a motivation. When we bring someone like that, it's controversial, and people watch controversy. In fact, I'll just close with this. Many years ago, I got a phone call from NBC, and they wanted to interview me on biological evolution. And so we're going to have this documentary show where we got people across the spectrum with different beliefs on evolution, and we've heard that you're someone that's got something to say about this. Tell us what it is that you believe. They kept me on the phone for 45 minutes. After the call was over, they said, Dr. Ross, we're not going to be able to use you. And I said, well, why not? They says, well, your view is just too reasonable. And so they featured a flaming atheist and a flaming young earth creationist engaging one another, highly controversial, but it was all heat and no light. And so I got bumped from the show. And my wife said, Hugh, you shouldn't have let them interview you for 45 minutes. You should have kept them guessing, and maybe they would have had you come on. And by the way, I've been even treated more harshly by the History Channel, where they actually had me interviewed for 45 minutes and then clipped 10 seconds and 15 seconds and made it look like I believed something that I didn't believe. So that happens too. And I've learned a lesson. Be careful when you get interviewed by the media where they're using a third party that goes out of business the moment the interview is over. That's actually a warning that you're probably going to be abused, because that's how they protect themselves from any kind of libel or lawsuit. So, hey, I didn't mean to get off on that either. But next week I want you to come back with, okay, I'm going to actually role play. Someone actually believes that the Earth is flat. I'm going to actually try to refute your case, so hopefully you get some good engagement. What's the second assignment? Geocentrism. So, and incidentally, I've done many debates with geocentrists on television. They're much better equipped to defend their position than young Earth creationists are. They actually have some significant scientists there, and the science they bring out is actually more difficult to refute than the young Earth position. So, but we'll start with the easy one first. Prove to people that the Earth is spherical and not flat. So, and be prepared to deal with things like the refraction of the atmosphere and the fact that the earth isn't exactly spherical, it's slightly oblate. So those are all these little technical details. Let me close this in prayer. Father in heaven, we do thank you for this amazing book you've given us, the Bible. Lord, we thank you that for thousands of years it stood as the only book that actually communicated the details of our universe. And Lord, we thank you that you've used this book to show that it has predictive power, the power to actually predict the features of the universe thousands of years ahead of what human scientists have been able to discover. And Father, I pray that we can use that insight from the Bible as a means to communicate the much more significant truths in the Bible about your role as the Creator and the Savior and the Redeemer. Lord, that this would be a stepping stone that we could use to show people that everything that the Bible's got to communicate, especially about the way we should live our lives, needs to be taken seriously. And Father, I pray that you'd enable us to actually use it as a means to draw people to humble themselves before you and give their lives to Jesus Christ. And Father, I pray too that you'd help us to be patient with people that want to check all the evidence. Lord, let's give them the time and the space to do that. Make us expert fishermen where we don't yank on the hook and lose a fish, but we keep that fish going until they actually get into our boat or until they actually become a follower of Jesus Christ. In Jesus' name, amen. Okay, thank you.
you.